this lecture of heat and mass transfer. This lecture is lecture number 4 of unit number 3, and in this lecture we are dealing with the differential derivation of differential equation which involves convection. So the objective, as I have discussed just now, that the objective are to derive the differential equation that govern the convection on the basis of mass, momentum and energy balances, and solve these equations for some simple cases such as laminar flow over a flat plate. And then the aim again, another aim is to obtain the non-dimensionalized convection equation and obtain the functional forms of friction and heat transfer coefficient. So as you can see, this is how we start our derivation of differential convection equation. Okay, so we derive the governing equation of fluid flow in the boundary layer. To keep the analysis at a manageable level, we assume the flow to be steady and two-dimensional and the fluid to be Newtonian with constant properties like density, viscosity and thermal conductivity, etc. Now let us consider the parallel flow of a fluid over a surface. This is the surface over which this fluid is passing. So we take the flow direction along the surface to be x and the direction normal to the surface to be y, and we choose a differential volume element of length. This is the differential volume that we are choosing for our study, and its length is dx and height is dy, and the unit depth in the z direction normal to the paper for analysis. The fluid flows over the surface with a uniform stream velocity v, but the velocity within the boundary layer is two-dimensional and the x component of velocity is u and y component of the velocity is v. So we notice from this figure that u depends u depends upon x and y. Similarly, v also depends upon x and y, and in a steady two-dimensional flow. Now we apply three fundamental laws to this fluid element, that is the conservation of mass, conservation of momentum and conservation of energy, to obtain the continuity, momentum and energy equations for laminar flow in boundary layer. So we first apply the continuity equation. Okay, so or you can say the conservation of mass principle. So the rate of mass flowing into the control volume is equal to the rate of mass flowing out of the control volume. The volume here, the control volume is the volume element that we have chosen for our study. Now note that mass flow rate is equal to the product of density, average velocity and cross sectional area normal to the flow. So the rate at which the fluid enters the control volume from the left surface is rho u into dy into 1. The rate at which the fluid leaves the control volume from the right surface can be expressed by this equation. So again this can be repeated along y-axis and substitute the result in equation 6.18 and we obtain this equation. Okay, so this is the equation that we finally obtain, and by simplifying and dividing this equation by dx dy into 1, we get this equation. Okay, so this is the conservation of mass principle, and this finally the equation that we obtain is also known as the continuity equation, or simply the mass balance for in case of an steady flow. In case of steady flow, okay, this equation is valid only for the steady flow. Okay. So next is the momentum equation. So a differential form of equation in the motion in the fluid velocity layer are obtained by applying Newton's second law of motion to it, to the differential volume that we have chosen for the study. And Newton's law is an expression for momentum balance, and as we know that it can be expressed as the net force acting on the control volume, and it is equal to the mass times the acceleration of the fluid element within the control volume, which is also equal to the net rate of momentum outflow from the control volume. So we express Newton's second law of motion for control volume like this, and it can be expressed as mass into acceleration in a specified direction, that is equal to the net force, that is the body and surface forces acting in that direction. So this is the net force which is acting on the body. Okay, and where the mass of the fluid element within the control volume equal to this value. Now we know that the flow is steady and two-dimensional. Thus, this value be equal to u xy, that is velocity along x-axis. The total differential u is given like this. Okay, so the acceleration can be expressed by this equation. Now further, let us further explore the momentum equation. So the force acting on the surface, we have calculated the acceleration. Now we have to calculate the force on acting on this surface. Okay, as you can see, these are the forces which are acting on the surface. From two sides the pressure force, and from the other two side the shear force. These are the forces which are acting along the body. Okay, so the total force, as you can see on this surface, the force is tau x plus del tau over del y into dy, and here it is tau, and this is rho p del p over del x, and this is p. So del p over del x. Now f on the surface equal to this value, and this is as you can see, by putting these equations, these values in the force equation, we obtain this value. So tau equal to mu del u over del y, substituting this equation, all the values in the equation 6.23, we obtain this equation number 6.28, which is equal to rho into u del u over del x equal to v del u over del y, that is equal to mu del 2u over del x square minus del p over del x. So this is the momentum balance in the x direction, and it is known as the momentum equation. Now we would obtain the same results if we use the momentum flow rate for the left hand side of this equation. Instead of the mass times acceleration, if there is a body force acting in x direction, it can be added to the right side of the equation, provided that it is expressed per unit volume of the fluid. So this is the you can see a nozzle, garden hose nozzle, on which the water is entering and it is leaving the surface. Okay. So the momentum equation, as we have seen, if along y-axis, similarly we can derive the momentum equation along the y-axis also, and thus if the pressure in the direction normal to the surface is negligible, and thus p equal to this value, then it follows that for a given x, the pressure in the boundary layer is equal to the pressure in the free stream, and we obtain that this is the velocity component of the free stream region in the flat plate are these values, and substituting these values into x equation gives us these values. Now let us come to the conservation of energy equation. Conservation energy balance of any system undergoing any process is expressed as, we have earlier discussed that energy entering and minus energy out is delta E of the system, which states that the changes in the energy content of a system during a process is equal to the difference between the energy input and energy output. During a steady flow process, the total energy content of a control volume remains constant, and thus delta E of the system is equal to 0, and amount of energy entering a control volume in all forms must be equal to the amount of energy leaving it. So the rate from the general energy equation reduces for a steady flow process, that is equal to this value. Noting that the energy can be transferred by heat, work and mass only, the energy balance for steady flow control volume can be written explicitly as this value. So this is basically the energy entering and energy leaving by due to the heat, energy entering and leaving because of the work, and energy entering and leaving because of the mass that is entering into the system or leaving into the system. So the total energy of the flowing fluid per stream of unit mass is given in unit mass terms, is given by this equation, where H is the enthalpy, which is the sum of internal energy and flow energy, that is equal to PE. Potential energy is given by this equation. Kinetic energy is given by this equation, that is V square by 2, which is equal to V square plus U square upon 2, is usually very small relative to the enthalpy, and therefore it is common practice to neglect them. Besides, it can be shown that if kinetic energy is included in the following analysis, all the terms due to this inclusion cancel each other, and we assume that the density rho and specific heat Cp, viscosity mu, and the thermal conductivity K of the fluid is this value, and we obtain the enthalpy as this value. So the conservation of energy equation that we have that we are utilizing here, let us consider this that we have earlier discussed. Now again let us represent these equation or these in terms of by applying on a control volume. Okay, so energy entering and out by mass is given by this equation, and repeating the same along y-axis and adding the result, net rate of energy transferred to the control volume by the mass is determined to be this value. So here del u over del x upon del plus del v over del y equal to 0 from the continuous equation. So further this equation simplifies to this value. Okay, and now repeating along y-axis the same energy can be obtained. So from the energy equation for the steady flow dimensional in a fluid, constant properties and negligible shear stresses is obtained by substituting these equation, and we obtain this value, which states that net energy convected by fluid out of control volume is equal to the net energy transferred into the control volume by the heat conduction. And the viscous stresses are not, if we do not neglect them, their effect is counted by the this equation, and the viscous or dissipation function is obtained after a lengthy analysis, and we are only representing it in the forms of only the equation. And then in case of stationary fluid, u and v are also 0, so the energy equation reduces and can be expressed into two-dimensional heat conduction equation, that is that we have earlier derived, and it can be represented by this equation. So for a flat plate, as we know that the continuity, momentum and energy, these are the continuity, momentum and energy equation, and with the boundary conditions which are given over here. Okay, so these are the boundary conditions that are utilized to solve the problem of a flow over a flat plate involving energy, momentum and continuity equation. Then again in order, but solving those equations are very difficult, so we utilize the Blasius solution of these problem, and this can be expressed in terms of a dimensionless similarity variable like this value. Okay, where this is u upon v is a function, then it can be called as a stream function, as we know that. And here it can be expressed as a stream function value like this. The velocity component becomes like this, and the other component can be expressed in terms of these values. So flow over a flat plate, the general solution of the flow over a flat plate can be given by this equation. And these are some of the values which are presented over here. You can study in depth when you try to, we will study, we are only concerned with the values. Okay, so this is the solution of the problem that we have obtained, and based on this equation, following are the values that has been that are utilized for the solution of this problem. And further, from the solution of this problem, we obtained that the boundary layer thickness is given by this equation, which is equal to 4.91 under root v upon nu x, where nu is the kinematic viscosity. And this can be represented in terms of Reynolds number after utilizing proper relationship used for Reynolds number. Okay, so from the solution of this equation we can obtain the shear stress along the flow, and it can be expressed by utilizing this relationship, and it is expressed after putting all the values of the solution. We obtain that this is the value of shear stress that is encountered in the flow over a flat plate. And it can be further expressed that the friction coefficient is given by this equation. Similarly, for in case of energy equation, this is the value that can be provided, and T or temperature of the surface and temperature of the ambient are constant. Substituting into energy equation, we get this value. And the temperature profile for flow over an isothermal flat plate are similar, just like the velocity profile, and thus we expect a similar solution for temperature to exist. Further, the thickness of the thermal boundary layer is proportional to this value, and which is actually can be converted into Reynolds number, and the velocity boundary layer, and thus the similarity variable is also eta, which is equal to this value, using the chain rule and substituting u and v, expecting from this energy equation gives this value. Okay, and again after putting the value of Prandtl number over here, we obtain this equation. So further simplification of this equation actually provides many more results, and it looks a little bit complex, but we don't have to remember all these expression. What we need to remember, we have to remember these expression only in terms of Prandtl number, in terms of Reynolds number, in terms of other numbers like Nusselt number and thermal diffusivity, in order to fully understand the flow field. And further Nusselt number can be expressed can be expressed using this equation. From the Nusselt number, it is clear that Nusselt number is a function of Prandtl number as well as Reynolds number. Okay, so numerically the temperature profile for different Prandtl numbers using the definition of thermal boundary layer, it is determined by this equation, and then we obtain the thermal boundary layer using this equation. Okay, so thermal boundary layer and velocity boundary layer are related in this way. So the summary of this lecture, we have discussed that velocity boundary layer thickness is this one local friction coefficient is this one, Nusselt number is this one, thermal boundary layer is this one. Okay, this is the formula that is utilized for these values. Okay, so the review question are here. First question is, what does the friction coefficient represents in flow over a flat plate and how it is related to the drag force acting on the plate? What is the physical mechanism that causes the friction factor to be higher in turbulent flow, and what is the turbulent viscosity, what it is caused by, and what is the turbulent thermal conductivity and what it is caused by. So these are the references. Most of the lecture is prepared using Yunus Essential book, Heat and Mass Transfer by Yunus Essential. But these other two books are also referred for the preparation of this PPT. Thank you for watching this lecture. Thank you all.